Good morning, on and all. Today we are going to discuss how DFS can be converted to regular expressions. DFS can be converted to regular expression. For example, this is a DFA. That means, as I told you in the previous class, here this is the start state and this is the final state. Here the regular expression corresponding to this is A. That is, here from the start state upon receiving A, it reaches the final state and the language exhibit is A, that is represented by this. And suppose that you have B here, this is represented by A, B star. Why? Here, after a single A, it reaches A and all subsequent B's will be accepted. That means 0 or more occurrence of B. That is linear closure. These things we discussed in the previous class. Now we are going to discuss how a finite domain node. Suppose that the transition diagram of an expression is given, then how that can be converted to a regular expression. So there are two methods for doing this. One is the Arden's method and the other is state elimination method. So at first we are going to discuss how state elimination method can be applied. For example, here there are some primitive steps you have to do by eliminating this. So first step is, if there is any incoming transition to the start state. For example, suppose that this is your start state and start state is represented by this, and suppose that you have something like this. That means suppose that you have Q1 here and this is the start state, and here from Q1 to Q1 you have what? You have a self loop, and that loop is also an incoming one. If there is any input symbol or input transition coming to the start state, you have to replace that with this is equivalent to, that means you are going to create a new start state Q0 and this is the original start state, and now you have to make this new state as the start state. Then you have give an epsilon transition to the new state to the previous start state, and that is 0 here. That means if you have an incoming transition to the start state, you have to do this thing. That means you have to make a new start state, and the outgoing transition from that new start state is coming to the previous start state. That means this is replaced. That means this is replaced with this. Why? Here you have an incoming transition. Now the second step is, if there is an outgoing transition from a final state, create a new final state and have an epsilon transition from the previous final state to the current final state. Suppose that you have say Q0 and suppose that Q1 is a final state and suppose that it is 0 and suppose that you have say 1. That means here this is a final state, and from this final state you have an outgoing transition to Q1. As this is having an outgoing transition, what you are going to do is, here you are going to start a new final state say QF and make this a non-final state and have an epsilon transition to this new final state QF. That's it. That's minor modification. That means if you have an incoming transition to the start state, you are going to start a new start state, and if there is an outgoing transition from the final state, you are going to create a new final state. And as you know, in a transition diagram or in a DFA or NFA, can have a single start state and you have multiple final states. Suppose that you have say Q1F, Q2F, Q3F. This is Q3F. Suppose that these are three final states. Suppose that these are final states, final state and final state, and this is a finite automaton, and here you have start state q0 and something like this. That means here for this you have a single start state, and suppose that you have multiple final states, and the minor modification you have to do is, instead of all these final states, you're going to create a new final state, say qf, and make it as a final state, and have epsilon transition from all these final states to the newly created final state, and make all of this null or non-final. Make all of this non-final. Make all this non-final. That you have to do. Okay. So these are the prerequisites for doing this. That means initially, if you have a start state which has incoming transition coming to that, you have to create a new start state and do the minor modifications. If you have a final state which has outgoing transition, there also you have to make some modifications, and if there are multiple outgoing transition, you have to make some modifications. Only once you do that, it's very easy to construct, or by state elimination method can easily do, or you can easily convert your DFA to regular expression. For example, suppose that you have say 0, and here suppose that you are having, say this is q0, this is not q0, suppose that our start state is q1 and this is q2, and 0 1, suppose that this is 1, and suppose that you have 0 here. Now I am going to convert this to its equivalent DFA, not DFA, regular expression. See here, for this start state there are incoming transition. That means here you have a self loop which is incoming, and from Q2 also there is an incoming transition. And as per rule number 1, you have to create, I am going to have a new start state Q0, and Q1 is there, and this is the original one. Q2 you have, that is final state, and 1 you have 1 here and 0 here. Okay. Now here you are going to have an epsilon transition from Q0 to Q1. You are going to have an epsilon transition from Q0 to, you have created a new start state Q0, and from that state Q0 there is an epsilon transition to the previous start state. Okay, now this portion is over. Now the second step is, if there is an outgoing transition from a final state, create a new final state and have an epsilon transition from the previous final state to the new final state. Here, see, from state Q2 you have an outgoing transition as well as you have another outgoing transition. So what you are going to do is, you are going to create a new final state Q3 and make it as a final state. Make this a non-final state and have an epsilon transition to the new final state. That means that step is also over, and step 3 is not applicable to us. That means step 3 is applicable if there are more than one final states. Here in this case we don't have more than one final state. Now see, what we are going to do is, we are going to eliminate all these intermediate states. That means you are not allowed to eliminate the final state and the start state. That means what input you can reach from the start state to the final state, that we are going to find. All the intermediate states we are going to eliminate, and I will show you how this can be done. For example, suppose that I am going to eliminate this Q1. See, this is Q1, and pictorially Q1 is represented by this. This is Q1. What are the incoming transition to Q1? That means here from Q0 there is an incoming transition, from Q2 there is an incoming transition, and from Q1 itself it is having a self loop. We have to take care of what are the incoming transition from other states. Here from Q0 you have an incoming transition. From Q0 there is an incoming transition labeled epsilon, and from Q2 you have another transition to Q1. From Q2 and the label is 0. These are the two incoming transition to Q1. And what are the outgoing transition? Again from Q1 to Q1, that we don't have, that is a self loop that we are going to treat like this. That means 0. This is the self loop. That means from Q1 to Q1 you have 0. And what is the outgoing transition? That means from Q1 to Q2 you have an outgoing transition. That means Q1 to Q2 you have an outgoing transition labeled 1. That means I am going to eliminate this Q1. As I am going to eliminate this Q1, I am going to have new transitions, or I am going to consider what are the incoming signals or what are the incoming transition to Q1 and what are the outgoing transitions from Q1. And incoming transition from Q1 include epsilon from Q0, 0 from Q2. That means from there is a transition labeled 0 from Q2, and there is an outgoing transition labeled 1 from Q1 to Q2. That is this one, and you have a self loop. Now there are two routes coming and there is one outgoing. There are two routes coming to a junction and one is an outgoing. That means now if you are eliminating this, there is a route from Q0 to Q2. That means if you are eliminating this, then there should be, that means there is a path from Q0 to Q2 and there is a path from Q2 to Q2. Okay, that means there is a path from Q0 to Q2 and there is another path from Q2 to Q2. And these two paths we are going to consider. That means from Q0 to Q2, for reaching here you have to use epsilon. Then you can have, you can wander here. That means you can stay over here, or upon 0 star, that means for epsilon it is coming here, and for 0 star it is staying here, and on 1 it is exiting and it is going to 2. That means from Q0 to Q2 you have epsilon dot 0 star 1, epsilon dot 0 star 1, and from Q2 to Q2 what is that? Upon reading 0 it reaches Q1, and for 0 star it is staying there, and on Q2 it will exit. That means epsilon dot 0 star 1 is simply you can write 0 star 1, 0 star 1, and Q2 to Q2, 0 0 star 1 is 0 0 star 1. That means there is a path from Q0 to Q2 and there is a path from Q2 to Q2. If you eliminate this Q1, you have to reinstate those paths. That means if you are closing this junction, there should be some path from Q0 to Q2 and there should be another path from Q2 to Q2. If you are closing this junction, you should have paths from Q0 to Q2 and from Q2 to Q2. That means here I am eliminating this. Now I have eliminated this, and there is a path from Q0 to Q2 and it is accepting 0 star 1. That means here there is a path and that is accepting 0 star 1, and there is a path from Q2 to Q2 which is accepting 0 star 1. That means here there is a path which is labeled 0 star 1. Okay, now you have eliminated Q2. Now I am going to eliminate. That means we are not allowed to eliminate start state as well as the final state, and now I am going to eliminate Q2. Going to eliminate Q2, and see here there is a, this is Q2. Okay, this is Q2. What are the incoming transition? That means here two self loops, one incoming transition, one outgoing transition. See, what is the incoming transition? It is coming from Q0, is coming from Q0, and it is labeled 0 star 1. It is coming from Q0 and is labeled 0 star 1. And there is an outgoing transition to Q3 which is having label epsilon, and there is a loop. That means here we have, this is when I am going to combine these two, this will be 1 or 0 star 1. 1 or 0 star 1. 1 or 0 star 1. Okay. Now, see, this is the loop and that is labeled 1 or 0 star 1. 1 or 0 star 1. Now, see, now if you are closing this or if you are eliminating Q2, there should be some way from Q0 to Q3, or if you are closing this junction, there should be some path from Q0 to Q3, and in that path it will accept, that means from Q0 to Q3, on accepting 0 star 1, it reaches this place, and for staying here, this will be that we can repeat any number of times. Okay, star followed by epsilon, and this one followed by epsilon means you have to eliminate that, and when you are eliminating this, this is 0 star 1 followed by 1 or 0 star 1 whole star. So this is the regular expression. This is the required regular expression for our original figure. This is the required regular expression for our original figure. That means before eliminate, this is very simple. This is a very simple technique, and once you do that, and I'll show you another example also. See, this is Q0. Suppose that it is 0, this is 1, Q0, Q1, and suppose that again it is 1, suppose that this again is the start state. Suppose that this is a regular expression. Now this is a DFA, and how this can be converted to an NFA. Here the start state and the final state are same. Start state itself is a final state. So you have to make some arrangements here. That means as the start state is the final state, you have to find out another start state and another final state. Why? Here the start state is having incoming transition, final state is having outgoing transition. So as per our first rule, I am going to create a new start state, say QS is the new start state, and I am going to have an epsilon transition to the final state Q0. Okay, now this is not having any incoming transition, but if you treat this as a final state, this final state is having incoming transitions. So now final state is having outgoing transition. So I am going to have a new final state, say QF, make it as a final state, and I have created an epsilon transition to that. Now for this, QS is the start state and QF is the final state. Okay. Now Q0, Q1, Q2. Now I am going to find out. That means now you have you are treating this as a non-final state. Okay. Now looking at this figure, now I am going to eliminate this Q1. What about Q1? So for Q1, what are the incoming transition? There are two incoming transition. One is from Q0 and the other is from Q2. That means from Q0 and the other is from Q2. From Q0 you have 1, and from Q2 again you have 1. And there is a loop, and that is also labeled 1. And what are the outgoing transition? Only a single outgoing transition to Q2. That means from here you have an outgoing transition to Q2 and it is labeled 0. So for this Q1, there are two incoming transition labeled 1, and one is from Q0 and the other is from Q2. You have a loop labeled 1, and it is a self loop, and this is going to the output, and there is an outgoing transition to Q2 labeled 0. Now, if I am eliminating this, there should be a path from Q0 to Q2, and there should be another path from Q2 to Q2. That means from Q0 to Q2, the path is Q0 on 1. This is on 1 it reaches here. For 1 star it is staying here, and for 0 it will go to Q2. And what about Q2 to Q2? Q2 to Q2 it is from Q2 on 1 it reaches Q1. For 1 star it is staying here, and for 0 it will exit. Okay. So for Q0 to Q2, now if you are eliminating this, now I have eliminated this. There should be two paths you have to reinstate. That means Q0 to Q2 and Q2 to Q2. What is Q0 to Q2? Q0 to Q2, you have 1 star 0, 1 star 0, and from Q2 to Q2, that means there is a loop. Again, that is 1 star 0. Now, see, now try to eliminate Q2. I am trying to eliminate Q2. So for that, what you have to do is, for Q2, there is an incoming transition from Q0. There is an incoming transition from Q0, label 1 star 0. There is an incoming signal or incoming transition from Q0, label 1 star 0. There is a loop for Q2 which is again 1 star 0, and there is an outgoing transition to the state Q0, and that is having label 0. Okay. Now, if you are eliminating this Q2, there should be a path from Q0 to Q0 going through Q2. That means, suppose that you are eliminating this from Q0 to Q0, the path is for 1 star 0 it reaches this 1 star 0 it reaches here. Then for another 1 star 0 it is staying here. 1 star for 1 star 0 it is staying here, and for the next 0 it will exit. And this is Q0 to Q0. There is no other paths you have to reinstate. That means from Q0 to Q0 you have a loop which is 1 star 0 followed by 1 star 0 star 0. Okay, 1 star 0 star 0. Now, if you are eliminating this Q0, what will happen? Now, you are in a position to eliminate Q0. Now, if you are eliminating this Q0, now Q0 is the state you are going to eliminate. Here you have a self loop that is 0 or. That means if you are clubbing these two, this will become or 0. Okay, or 0 or 1 star 0, 1 star 0 star 0. Okay. Now, 1 star for from Q0 to Q0. Now, see, from QS, there is an incoming transition labeled epsilon, and from Q0 to QF, you have another epsilon transition, and this is the loop. Now, what you have to do is from QS to QF, QS to QF, you have to reinstate the path, and from QS to Q0 you have epsilon followed by this one you have to repeat for staying in Q0, or it is 0, 1 star 0, 1 star 0 star 0, the whole star followed by epsilon. That means epsilon dot epsilon means this is 0 or 1 star 0 followed by 1 star 0 star 0. So this is the required regular expression. That is the required regular expression, and in this way any deterministic finite automaton or non-deterministic finite automaton can be easily converted to its equivalent regular expression. So try more examples, and once you do more examples, you will be thorough with this. For converting DFA to regular expression, the first method we discussed is state elimination method, and today we are going to discuss another method which is Arden's method. And this Arden's method is depending on Arden's lemma. Arden's lemma is if you have a regular expression R is equal to Rp plus Q, then that may be replaced by R is equal to QP star. This is called Arden's lemma. And using that, we are going to have an equivalent expression for this. This is the first example. Using an example is very easy to do. And see, from start, the regular expression corresponding to this is Q1 or Q2. Here you have two final states. Either you have to reach Q1 or you have to reach Q2. So this should be the final regular expression. That means all input symbols or strings which will make you to reach Q1 or Q2 can be accepted. So that is the regular system. That means we have to write either Q1 or Q2. If Q2 is the only final state, then this one be here and R is equal to Q2. Now I am going to have expression for this. Expression for Q1, Q2 and Q3. We have only three states Q1, Q2 and Q3. I am going to have going to write expression for that. And see the expression for Q1. Q1 is equal to, what are the incoming transition? We have to check. What are the incoming transition? Only one incoming transition. That means Q1, after accepting a 0, it will reach Q1. That means Q1 is equal to Q1 on accepting 0, it will reach Q1, or without accepting anything also you can reach here. Why? Q0, Q1 is the start state. As the start state itself is a final state. As the start state itself is a final state, you have to include epsilon also. That is, from Q1 on 0 you can reach Q1, or without reading any input symbol also you can reach Q1. That means as this is the start state, from Q1 to upon reading anything, that means for the start state we have to include this epsilon also. Okay, so this is the first equation number 1. And for Q2, what is this? For Q2 is Q1 on accepting 1. That means Q1 on accepting 1 or Q2 on accepting 1. Q2 on accepting 1. This is second equation. And what about Q3? Q3 is equal to Q2 on accepting 0. Q2 on accepting 0. Q2 on accepting 0, it reaches Q3. And Q3 on accepting either 0 or 1. Q3 on accepting 0 or Q3 on accepting 1. That means Q3 on accepting 0 or Q3 accepting 1, it reaches the state Q3. That means now you have Q1 or Q2. That means the final expression is Q1 or Q2. That means either you have to reach Q1 or Q2. As Q3 is not a final state, there is no need to reach there. Q1 or Q2. Now, as per Arden's lemma, R is equal to RP plus Q. This is, treat this as R, and this Q1 is also R, and this is P. R is equal to RP plus epsilon is, this is Q. Epsilon is Q. That means R is equal to RP plus epsilon. R is equal to RP plus epsilon. Then you can replace that R with R or Q1 with, that means from here R is equal to RP plus Q. Then Q1 is equal to Q1 0 plus epsilon. Then that Q1 can be replaced, or R can be replaced by QP star. R1 is Q1 equal to what? QP star. What is Q? Epsilon into what is P star? 0 star. Epsilon followed by 0 star is 0 star. So Q1 is 0 star. Now what is Q2? Now we know that Q1 is 0 star. So I am going to write this. That means from here Q2 is equal to Q1 1. We know that Q1 is 0 star. 0 star 1. 0 star 1 plus Q2 1 plus Q2 1, or Q2 is equal to, that means interchanging this, Q2 1 plus 0 star 1. Okay. Now this again is in which form? R is equal to RP plus Q. This is R. This is R. This is P, and this is Q. RP plus Q. This can be replaced by R is equal to QP star. R means Q2 is equal to what? Q2 is equal to QP star. Q is 0 star 1 and P star is 1 star. That is 0 star 1 1 star. So you got Q2 also. You know what is Q1 and you know what is Q2. So there is no need to calculate this Q3. Why? Our regular expression R is the sum of Q1 and Q2. That means here R, the regular expression R is equal to Q1 is 0 star or what is this? 0 star 1 1 star. 0 star 1 1 star. 0 star, that is this is the expression 0 star or 0 star 1 1 star. So if you want you can simplify this also, that is this is equal to 0 star, take this as common, epsilon or 1 1 star, which is epsilon or that means 1 1 star. Here this is 0 occurrence of 1, that means you can have 0 star 1 star. 0 star 1 star, that is a simplified form. In this session, we have discussed two methods, the state elimination method and the Arden's method for converting a DFA to its regular expression. And with this, I am concluding this session. Thank you.